Tim, we have 24 attendees right now, plus our panelists. So it's just 6:30. So as always, we give people some time to get on.
Oh, great. Okay. It's 6:30. And so we're going to just give everyone a couple of minutes to get going here. It's uh, great to be back on a webinar. It's been a while, and this is a really significant day in my life, the anniversary of the blizzard of 1978, which kind of launched me in this direction into meteorology, even though I was obsessed with meteorology even before the blizzard of 78, but when the snow turned into rain and then the sun came out on Cape Cod, while I saw 40 miles away there was a winter sort of hurricane taking down houses. I mean, it wasn't pretty in Scituate, Massachusetts, which is just uh, across the bay from me. It was just confounding how such a powerful storm. I I didn't understand how the sun could be out on Cape Cod. I've since learned that it was an occluded front. It wasn't really the eye of a storm. So that's one of the things that got me going into weather. And Bruce Anderson is here from Boston University, and he's going to explain to us a little bit more about how climate change is adding to the extreme events. Seems like we're getting more and more extreme events, and certainly in the last week and all winter, we've had so many extreme events, especially what happened in California in the last couple of days. And there was a blizzard of 24 in Nova Scotia. That was an extreme event with up to 150 centimeters of snow. Let's see, there's 2.54 centimeters in an inch. So that's a ton of inches of snow from a storm that also did something like what the blizzard of 78 did.
Hey, I
So
didn't even hear about that one, but
it was a retrograding storm. So these storms that are the worst storms in New England, they come up and like looks like they're going by, and then they kind of come back at you. And they do this what I call the blizzard loop because they get caught in the upper level low, and it looks like they're going in circles. Sometimes it's a case where the low redevelops to the west on an occluded front or a triple point or something like that. But in the case of the blizzard of 78 and the blizzard of 2024 in Newfoundland, I mean Nova Scotia, it got caught in the upper level low and kind of did a circle and then went out. And the storms in California have behaved sort of similarly. So if you add the global warming, the increased moisture, and the fact that you get these storms that sometimes last 2 or 3 days, it's tremendous.
And stall out that you're really in trouble.
Yeah. So in New England, sometimes the hurricanes are less impactful because they last a shorter time.
Yep.
Of course, we haven't had a hurricane in 1938 since 1938, but it's only a matter of time before something like that happens again. So time we got 6:33. How are we doing for participants? I guess I can get this view going. View gallery. I don't know if I want to see the whole gallery. Let's see. It looks like we have 38 participants.
We're up to 30. Yep, 38.
All right.
Keep going, everybody.
I'm willing to wait till 6:35.
So while we're waiting, Bruce, why don't you introduce yourself, where you grew up, and maybe what got you sort of down the lane of studying climate and weather, and how you came to Boston?
I'm now a professor at Boston University. First 10 years were Boulder, Colorado. Both my parents are atmospheric scientists.
Oh, wow.
So I knew about the field. Neither of them are climatologists. So my mom does effectively the ozone hole, and my dad, if you were to do it, would be if you were familiar with either solar weather or solar weather or northern lights. But I knew about the field because they both worked at National Center for Atmospheric Research, and then I moved out here, and so I know the neighborhood. Eventually went to California for 8 years, UC Santa Barbara, UC San Diego, and then made my way back here. So been here since.
You're a full-blooded atmospheric science.
Oh yeah, absolutely.
Scientist.
We can't talk to each other. Dad does electricity and magnetism. My mom does radiation, and I do dynamics.
Oh my goodness, what a tremendous upbringing.
So we can't talk to each other.
What do you mean? What does that mean?
Well, as I said, one of them does electricity and magnetism. One of them does radiation. and I do dynamics, and none of them relate to. I mean, so.
Was there any specific event when you were a child outside of your parents being atmospheric scientists? Anything happen in Boulder? Any specific storm or event
No,
or anything?
no, I just knew the field well enough, and knew what was coming down the pipe. So mainly because they knew where the community was going, at least as far as climate goes. So I was always very familiar with it growing up.
I was not that familiar with it, but being on Cape Cod, just seeing all the different storms,
Yeah.
and today, the anniversary, 46 years ago. Wow, I can't believe it. Still remember exactly where I was when they put us on the school buses to go home. All right, so about 6:36. Well, I guess we can get started. Well, thank you everybody for joining us to the webinar series. I'm Tim Kelly with Professor Bruce Anderson, and Bruce is going to give us his take on the causes and consequences of climate change, especially how extreme weather is becoming more significant seemingly every year here in the Northeast. Take it away, Bruce.
Of course. So I'm going to only spend a brief amount of time on the causes. And I'm going to do that verbally without visualization, because I think most of you would rather see discussion of sort of what we can expect in the next decades, what our kids are going to expect, what our grandkids are going to expect in the region. So I guess I'll pull up the slide deck, although I'm going to talk to it a little bit before showing the.
So you have screen control?
Yep.
Good. Great.
So a few caveats, not really caveats. What I'm going to present today is not my own research. It is based upon what in our community we call assessments, where the climate community comes together and assesses or synthesizes sort of the state of the knowledge of the community. So do be aware that this is effectively a synthesis of what the climate community understands, and in some cases it doesn't understand, although I won't present a whole lot of that. And I've been involved with these since about 2006. A lot of these actually come from my first assessment that I participated in, which was the new Northeast Climate Impacts Assessment run through Union of Concerned Scientists. I've also done assessments for Cambridge. One of the more recent ones was called the Boston Research Advisory Group, which did an assessment of climate change impacts that ultimately was used to change design codes for Boston. It was popular enough that other communities wanted in and wanted to know what was going to what the influences on them were going to be. So we now have a Greater Boston Research Advisory Group. And it's not just me that's participating in it. It's not just people from the Northeast. The US requires impact assessment every 4 years. The last one, I think, came out in 2020. It's for all the US, but they do have a section just for the Northeast. So do be aware this isn't my own research, my own opinion. This is effectively a distillation of what the climate community as a whole understands about climate change, as well as its impacts on the Northeast. The other thing I will say, a lot of you are probably familiar with weather forecasts. So I'm sure lots of you know about the National Oceanographic and Atmospheric Administration. They do all of the hurricane forecasts. The National Weather Service is under them. Effectively, the data that goes into these assessments is drawn from those same agencies. So NOAA not only runs weather forecast models, they run climate change models. You've heard of National Center for Atmospheric Research out of Boulder. They do very basic science and improving weather forecast models, but they do the same type of science improving climate change forecasts or models. Out of Europe, ECMWF, which is the European Center for Medium Range weather forecasting. They produce all the weather forecasts for the European regions, but they also have these same models running for climate change, UK Met Office. So I just want to emphasize that this isn't sort of one-off kind of thing. All the agencies that are doing the weather forecasts are also producing these climate forecasts that go into the assessments. So I'm going to just start in. I'm going to start in provocatively. So throughout this, I'm going to have a few pop quizzes. And the first pop quiz is this one. How many of you believe in the theory of human-induced global warming? And just to put it on the table, that's the theory that the general warming of the globe since about the mid-1900s is attributed primarily to the emissions of heat-trapping gases arising from human activity. So the figure to accompany this, the x-axis down here is starting in about 1800, and we're up to about 2017 in this figure. And these are changes, and the units here are Celsius. If you want to put them into Fahrenheit, just multiply by 2. And so the question is, of the warming that we've experienced, unfortunately, I got to get rid of this. This goes up to 2017. Currently, we're in 2023. We're right about where my arrow is. So the question is, and I don't know how we want to do this, how many of you believe that this warming was induced by human emissions of heat-trapping gases such as carbon dioxide, methane, nitrous oxide? I guess I can't do a raise of hands.
I got the chat open. If people want to join in the chat, we can.
I can't see the chat because
I'll relay it. So far, I don't see anything in chat.
Okay. Well, the other option is that it's not. You don't believe that this is due to emissions of heat-trapping gases.
Chat is disabled.
Yeah, I tried to enter something and it's disabled.
Okay. Well, you guys work on that. The third option
we will
is
work on that.
No. And I'll give you the right answer. The right answer is it's a trick question because this is a theory. As a theory, it is no different than the germ theory of disease, no different than the theory of gravitation, no different than the theory of continental drift. It's no different than theory of evolution. Because scientifically, and this is how we're phrasing it, a theory is a well-accepted understanding that explains observations supported by experimental evidence and physical understanding of the phenomenon. And it also has to be able to make not just explain observations, but it also has to be able to make predictions. So it's not, if you went to the dictionary, you would get conjecture, guess, speculation. Those we call hypotheses. And effectively, the theory of human-induced global warming is a scientifically accepted theory. So as an example, I'll just do this quickly. If you actually go and survey the climate community has about a 97% consensus that the warming over the last 50 years is due to heat-trapping gases resulting from human activity. That turns out to be more than if you went to the medical community and asked them whether cigarettes cause lung cancer. That sits around about 95%. So it's a very well-accepted theory within the scientific community. So I'll go over a brief explanation of how what eventually started as a hypothesis became a theory. It turns out that the hypothesis that carbon dioxide could influence our climate was actually hypothesized 200 years ago, mid-1820s. It was hypothesized that carbon dioxide could absorb outgoing energy in the form of radiation, keep it within the climate system, and effectively warm the planet beyond what we just get from our own sun. And that was then observationally proven in the mid-1800s. And then there was a lot of development around the fact that carbon dioxide and water vapor could actually absorb radiation that's emitted from our planet. The biggest next step came in the 1960s. There were two things. advancements. One was an observational one. Somebody started, Charles Keeling, started measuring carbon dioxide on the big island of Hawaii. And it was the first sustained observations of carbon dioxide. And since he started observing them in the 1950s through today, the concentrations have risen continuously from about 320 parts per million. So for every million molecules in a volume, 350 of them are carbon dioxide molecules, to now 420. And that turns out to be about a 30% increase over what was in the atmosphere prior to the Industrial Revolution. So that was the observational evidence that carbon dioxide certainly was increasing in the atmosphere. The other thing is we finally got powerful enough computers to start to model what those increases in carbon dioxide could do to the climate system. And I will say that these models, or these computers, probably took up a hangar's worth of space, or at least a very big room, and had less computing power than your smartphone. But they were enough that they could start making actual projections. And their projections initially were, worst case scenario, the worst we could do is maybe double the pre-industrial carbon dioxide concentration. So I've worked with parts per million initially prior to the Industrial Revolution. Concentrations were about 280 parts per million. Back in the 1960s, the worst, the absolute worst, they thought that concentrations could get to was doubling to 520 parts per million. And they made a calculation. And it was rough, but it was for the whole globe. So we didn't need to know what was happening in any specific location. And it was about 2 degrees Celsius, 4 degrees Fahrenheit above pre-industrial concentrate, or the climate prior to the Industrial Revolution. And it turns out that that answer, that sort of fundamental answer that we arrived at, at least the community arrived at, in 1960 has not changed. We've gotten a lot better computers. We have a lot better idea of what's going to happen regionally. We've introduced a few new physical concepts, and I'll highlight those, but they've never fundamentally changed that the expectation that for a doubling of pre-industrial carbon dioxide, that the globe will be about 2 degrees Celsius or 4 degrees Fahrenheit warmer. The one thing that has changed is that now that doubling of carbon dioxide is not a worst case scenario, it's a best case scenario. It's actually going to be relatively difficult at this point in the next 80 years to prevent carbon dioxide concentrations from staying below 520. The worst case scenario now is not a doubling of concentrations, it's a tripling to something like 900 parts per million. And so when I go through here, I'll talk about what we call low emission scenario. That's something that gets us around 520 parts per million. High emissions, that gets us somewhere around 900 parts per million. So that's where we're headed. I'll just start by saying that indeed, even historically, we're already seeing. Why is my thing not moving forward? Oh, there. We're already seeing changes in our climate since the 1970s. Our temperatures are currently about 2 degrees warmer. One way to and our winters are 4 degrees Fahrenheit warmer than they were in the 1970s. To some extent, I'll do what's called migrating climates in a little bit. We now have a climate today in the Northeast that would have been Philadelphia in the 1970s. Obviously, snowpack is decreasing. If you try and go and do any pond hockey, which my kids love to do, you don't want to send them out there because the ice just isn't thick enough. I think they got 1 day of pond hockey in last year, and they've only gotten 1 day of pond hockey in this year. So I don't know how many people grew up in the region playing pond hockey or going cross country skiing. But it's a very different experience even now. Extreme summers are definitely getting warmer. If you do any planting, you can now plant very different plants in your garden than you could have 30 years or 40 years ago. And certainly spring is coming earlier and fall is coming later. And summers are lasting longer and winters are lasting shorter. So these are all observed outcomes that we're already seeing. So what's the projections? So here is the black line is our observed increase in temperatures in the Northeast. Again, this is a change in temperature. It's not the actual temperatures. And then these are projections over the next 100 years. And I'll just emphasize one thing. So this is, I'll emphasize two things, I guess. Under that low emission scenario where we only double carbon dioxide in the next 80 years, our region is going to be about 5 degrees warmer than it was back in the 70s. High emission scenario, closer to 9 or 10 degrees Fahrenheit. So think of it as what would have typically been an 80-degree summer day is now a 90-degree summer day. But this, I haven't posted the emission scenario, but for at least the next 50 years, it doesn't really matter what we do with emissions. So the way we phrase it is we've already bought ourselves an unavoidable warming up through the 2030s, 2040s. Really where our decisions matter, globally as well as regionally, is after that period. So this is based upon what we've already put into the atmosphere. It's going to stick around. It's going to produce sort of a warming of the Northeast. It's unavoidable at this point. But where our decisions really matter is the last half of the century. And that's what differentiates whether we end up here or here. And just a rule of thumb, and I'll highlight this throughout, that under the low emission scenario, the impacts are about half of the high emission scenario. So instead of warming by 10 degrees Fahrenheit, they warm by 5 degrees Fahrenheit. So that's just the average temperatures. We can do a lot of other, we can also start to look at sort of the characteristics of our weather, and that's my focus today, just because I think that's most important for this community. So the way I phrase this is that there's going to be a change in our climate, as well as the changes in the extremes that we experience day in and day out in the form of weather. So just as far as our climate, and again, I'm going to emphasize, this is all based upon consensus of the climate community. It's not a basis of, it's not my own opinion. So given that 10-degree increase, this is for the high emission scenario, if our temperatures get about 10 degrees Fahrenheit warmer than they currently are, what climate would Massachusetts most resemble? And I wish I could get audio because it's a lot more fun to do this way.
Okay, we've got some people. One person just Tamara said Georgia. We've got one answer coming in. I think the chat's starting to function. What?
Georgia.
Yeah.
So effectively, our climate would be somewhat like Georgia. Okay. Any other?
The chat is working, I think, for everybody.
Yeah, there was a bunch of chats. There was about 11 in there. They
Yeah.
had to do with
we've got the 2 North Carolinas. We got a Virginia. We got a North Carolina, Washington, D.C.
We're already at Washington, D.C.
We're already at Washington, D.C.
Yeah, we're already at Washington, D.C.
How about Myrtle Beach? That's my guess.
Well,
Miami,
here you go.
Florida, Miami. We got
Yeah.
a Miami, New
Well,
Jersey.
that one's the correct one.
Miami is the correct one.
Yeah, so if at least in summer,
Wow.
if we take into account
Miami.
our average summer temperatures of 78 degrees Fahrenheit or close to that, and add on 10 degrees, we now have the same climate in, at least under the high emission scenario, we will have the same climate as Miami. And we're effectively moving our entire state 1,200 miles to the south.
You said just summer.
Yeah, it is summer. It'll be winter too. Maybe we'll have a bit more of a seasonal cycle than
So we don't need to
Miami
move to
would,
Florida.
but at least our summer would be equivalent. So there's no, what is the, yeah. And I'll show some impacts of that in a second. Take a place like Arizona, and it becomes Kuwait. So we're geographically altering our climates effectively. We have analogs for what our climate is going to be like, and it's under this high emission scenario, our summers are going to be like Miami. And it doesn't just apply to temperatures. It's also going to apply to intensity of precipitation. And so I'm just doing temperatures. So now as an example for this, what does that mean as far as our seasonal cycle? I'll show two more as far as temperatures. I'll skip this one. So it also means our extremes are going to get a lot worse. So one way to measure climate is what's the change in the average. But another way to measure climate, because climate is just statistics, you can also ask, well, how frequently is it really going to be miserable? And so this is showing the occurrence of, and you might not be able to see the gray line. This is the occurrence of numbers of days that hit 90 degrees or historically. And let's just jump to this one. This is at the end of the century. This is high, or the low emission scenario. So it goes up from 10 to about 30. Or this is the low emission scenario. That then jumps to about 60. So again, there's a rough doubling of the number of hot days. But here's the key. None of these 90-degree days are going to be in January. So if you then just look at extended summer, let's say May, June, July, August, September, that's 150 days. If you take those numbers and look at how often these occur over that sort of 150-day period, in the high emission scenario, 1 in every 2 to 3 days is going to hit 90 degrees. We can also ask the same question about days over 100. Currently, or historically, maybe one day out of the summer would hit 100. You do that now under the low emission scenario, well, there's a 6-fold increase between here and here. There's a 24-fold increase from here to here. i.e., if you do the same division by 150 days, you're looking at once a week for 5 months straight that temperatures are going to hit 100 degrees. And it's not just going to be that they hit this. You're going to get a weather system that's going to come in. It's going to be 97, 98, 99 for a couple of days. Then it's going to hit 100. Then it's going to back down. And then maybe you'll catch a break and it'll be in like 89s or something. And then like every 2 to 3 days, it's going to be over 90. So that's the expectation. And just to put this in context, it's Miami. Think about whether you're going to be hiking in the Blue Hills, whether you're going to be running along the Esplanade in the summer when it's hitting for 5 months straight 90 degrees, and then obviously every other week or every week, somewhere in there, it's going to get up to 100. So it fundamentally changes what we can do in the Northeast, especially during summer. And I'll get to winter in a little bit. But the extremes here are going to be pretty miserable. And I'll just throw this out here. So this is 5 months straight of this. I'll go to France, Western European country, 21st century, 2003, France in particular, but Europe. They had just effectively a week of temperatures in the high 90s. They didn't break 100. Anybody want to guess the excess mortality in France for that 1 week period?
Guess what?
The excess mortality, effectively heat deaths, from that 1 week period, where temperatures never broke 100. but they were in the high 90s.
15%.
I don't know. I only know absolute numbers because I don't know what the average death rate is.
Someone guessed over 500.
500
3,000.
people. Anybody else want to chime in?
3,000. 15,000. But we don't know the population or the percentage.
Don't worry about the percentage.
Sounds like a difficult
50,000.
thing. 2,500.
50,000
50,000.
excessive deaths from a 1 week heat wave in France and Europe. Russia had something in 2010, 70,000 people. Excess deaths of 70. I mean, these things are, especially if you don't have air conditioning. Everybody in the South has air conditioning. A third of our buildings have air conditioning in the Northeast. So this is the expectation. And so there is certainly physiological, but also social consequences for this change in our climate. I'll skip the next one. The other change, as was mentioned, is intensity of precipitation. So this is actually a radar image in New York for a big storm that hit in 2014. Heavy precipitation in New York City. So this was summertime. Turns out that the warmer the air gets, the more water vapor it can contain. And then when that water vapor eventually condenses out, leads to heavier and heavier precipitation. And so I use that analogy. It means that when we get precipitation here in the Northeast, it's going to be equivalent to the type of precipitation, especially in the summer, because we get most of our precipitation in summer because it's warmer. Our rainfall rates are going to be equivalent to, again, somewhere in the Southeast, maybe not Miami, but not going to be that different from South Carolina, Miami, Fort Lauderdale. And it's a question of whether our infrastructure is capable of handling that. And certainly New York's infrastructure wasn't. If you've seen any of the images coming out of California, their infrastructure is not capable of handling it. But this next figure is not great. But if you were to, this multiplier is how much heavier does our precipitation get for high precipitation events. So the really heavy precipitation, when it really does rain, how much heavier is the rain? And this is somewhere about 50% heavier under low emissions, but we're looking at something like 2 to 3 times as heavy in the Northeast, and we're already experiencing that. The Northeast has had the highest increase historically of anywhere in the US of rain in the form of heavy precipitation. There's been a 70% increase in heavy precipitation events historically. So not only is the frequency of heavy precipitation increasing, the actual amount that's falling is going up, is 200%, or twice as much, 3 times as much. And again, it comes down whether our infrastructure can handle that kind of stuff. As I said, the example in New York City certainly couldn't. What's going on in California, it can't. And so we're really going to have to what we call adapt. Our infrastructure is going to have to be much more resilient. Does anybody remember the one that, I guess it was a hurricane or remnants of hurricane that hit Vermont and just wiped out, I don't know if it was 2018, just really devastated a lot of their country roads. Anywhere there was any kind of terrain, roads started to get washed out. So, but that's, again, an expectation.
That was Irene, and it's happened about twice since then also.
Yeah. Anywhere there's terrain is really susceptible. So again, it's not that it's just a change in the occurrence or the likelihood. And these type of events are just going to become more likely because there's just more water in the atmosphere to fall out. Ironically, while there's more rain and more intense rainfall to be expected, it turns out that as temperatures rise, because air can contain more water vapor, evaporation rates So when it's not raining, things really start to dry out much more rapidly. And in fact, the frequency of rainfall is actually supposed to go down in our region. So when it does rain, it rains more intensely, so flooding is more likely. But unfortunately, because the likelihood of rain goes down, as well as the amount of water in the soils that evaporates into the atmosphere increases, the likelihood of droughts increases. And so this is, I won't spend too much time on this. How often do we get periods of dry days? I mean, right now we're going through I don't know what the spell is, but we're going to go a whole week or so without any precipitation over the next coming few days. But in summer, it's going to be the same thing. And so the expectation, I won't go into the numbers, is that periods of no rainfall are going to increase. And then on top of that, when it doesn't rain, more water is being dragged out of the soils and into the atmosphere. And so we're actually going to start to experience droughts in our region that are equivalent, maybe not to California per se, but water availability is going to become an issue for us. So that's what the next figure shows. So not that it matters. This is the number of short-term 1 to 3 month low water availability droughts over a 30-year period. So we really, maybe in 5 years out of 30, we actually have droughts currently. We're just not a water limited place. We've got water available to us for our ecosystems, for drinking, for agriculture. But if anybody's been around and you haven't been allowed to water your lawns, under the high emission scenario, you'll see all these reds, 30 out of 30. That means every single year there's going to be some short-term drought, 1 to 3 months, where, yeah, you're not going to be able to water your lawns. And so water is going to be a resource that we're actually going to have to start contemplating that we really have never contemplated before. So that's one. Another outcome is not just the temperature influence on temperature, but the influence on resources. Where do we allocate our resources? Do we allocate it to our lawns? Do we allocate it to agriculture? Do we allocate it to drinking, clean drinking water? And so issues that we've never had to really have not conflicts, but just discussions about are expected to come to the fore. Okay, so so we're going to start getting more droughts. We're certainly going to start getting more extreme precipitation events when it does rain. We're going to have more extreme temperatures, particularly when we get heat waves. And the likelihood and the intensity of heat waves is going to go up. But there's other things, just our lifestyles. I mentioned before. Oh, I'll do one more extreme before I did this. Okay. So for people in the coastal communities, another thing you've got to start thinking about is flooding. So I'll do another pop quiz. So Hurricane Sandy hit our area. We got off really easily because it hit at low tide. So New York got hammered because it hit them 6 hours earlier during their high tide. By the time it reached us, we were at low tide. And even with low tide, we missed being inundated. So effectively, the main barrier for inundation in Boston is there's a overflow dam effectively underneath the Museum of Science, or right next to it. We missed overtopping that by 3 inches. Otherwise, all of the Charles would have flooded. East Cambridge, where they have a major electrical plant, would have been inundated. It would have been really, really bad. We missed by 3 inches, and even that we missed because we were at the low tide as opposed to the high tide. Now, we consider that type of flooding event to occur about once in every 100 years. It's called a once in a century flood event. And in fact, we design all of our flooding infrastructure currently to withstand a 1 in 100-year event. And it worked, at least for us. It didn't work for New York. So there's an expectation that as the globe gets warmer, glaciers on land, on Greenland and Antarctica are going to start to melt. I'll show this in a bit. At least locally, that's going to produce about 5-foot sea level rise, just base sea level. So now you throw Hurricane Sandy, or well, if you ask then, with that sea level rise and a high tide, instead of a storm that's a 1 in 100-year storm, which Sandy was, how often are we going to overtop our defenses? So the question becomes, how often we barely made it out of Sandy, which was once in a 100-year event. With that 5-foot sea level rise, how often are we going to overtop our current defenses?
So far, we've only got we got a 5-year, we got a 2-year, we got a 4-year. And I'll just add in that Portland, Maine just had 2 of their highest levels in 5 years, twice in the last 4 weeks.
Yep.
2-year, 10-year. Beth says 2. Donald says 10. NHCOG says 5, but then changed to 2.
Okay. No.
So the answers are they average around 4.
Yeah. Well, it's probably every year, and that's
Every year.
conservative.
You're all too high.
Yeah. Just a minor, not a minor, but just a typical wind-driven storm coming off the Atlantic would produce a storm surge enough when you add that 5 feet, especially if it hits at high tide, to overtop.
Right. The barometer has a lot to do with that too.
Yeah, but just a standard storm would do it. A typical storm once a year would overtop our current defenses.
Yeah.
Given that sea level rise. And so this is the projection of sea level rise for the Northeast. And as I said, it's actually, this was from so here's here's the projection. This is mainly based upon not so much.
I'm muted and my video is off. The animals are loving this.
Yeah. Mainly this is actually what we call thermal expansion. The water just expands because it's warmer. Half of the current sea level rise through here is just warmer water, is taller water, it's expanding. And half of it's glacier melt. But going forward, this is all going to be glacier melt from Greenland mainly. And these days, this was conservative in 2015 or so. The most recent stuff we've done for Boston is saying about 4 to 5, somewhere right in here. And that has to do with various things. When Antarctica melts, its gravitational pull on water weakens, and so that water starts to rush towards the northern hemisphere. There's a few other things, but the latest science puts it about 5 feet. And so that's where we get that 5-foot rise. And if you want to see what happens, at least to the common, as I said, our barriers currently confine the 1 in 100-year storm to the Charles River. That's what they're designed to do. But every time they get the sea level rise, well, the storm surge exceeds that. This used to be the Back Bay for a reason. It's going to turn back into a bay. It's not going to be Katrina-like, and New Orleans sits below sea level. But yeah, you don't want a basement apartment on Newbury Street.
Right. The Back Bay essentially is a swamp that they filled in.
Yeah, and it's just going to refill.
How about BU? Are you guys going to go under too?
No, I think they do have the line prior to the infill of the Back Bay. But yes, if this doesn't get protected, yes, basements of BU are going to get flooded. All of its heating and all of its electrical components, because back in the day we built everything in the basements, and now they know to put everything on the roof. But it's really hard to retrofit stuff. So again, this is the constant. Without reinforcing our defenses, this becomes a once in a year occurrence. Even and I don't have it here, but even currently, all that new really expensive waterfront property, where is it? In Harbor? Is it the Harbor Front? What's it? Boston did all of this renovation, and anyways, $1 million hotels, new restaurants, and they get flooded on what is called the king tide, the highest tide of each month. It starts to overlap the sidewalks and stuff. So they're already facing this, even on just high tide without any kind of storm surge. Okay, so there we go. I won't really. So now I mentioned, at least in our neighborhood, that once temperatures in the summer in particular start hitting 90, 100 degrees, concept of hiking outdoors, running on the Esplanade, or even just mountain biking become onerous, or at least unpleasant. But it's not just the summer. So I've done the migrating climates before. I did it for Massachusetts, but New Hampshire starts to show up as sort of these portions of the Southeast, which needless to say don't receive a whole lot of snow. And when they do, they don't receive a whole lot of snow, because especially in winter, instead of falling as snow, it falls as rain. The temperature's warm. And we've experienced that here this summer, or this winter. A whole lot of storm systems, not a whole lot, but a few storm systems have come through, and there's nothing on the ground, at least in the neighborhoods that I'm part of. I don't think it's true for Blue Hills, except for where you make snow. I just don't think you guys have any snowpack. And so we could ask, well, how frequently is snow going to be found on the ground? And it turns out not very frequently. So what this is asking is how many days out of a given month in winter, so 30 days out of 30 would be the whole month, has snow cover. And this is current conditions. And so these regions have, at least through the winter season, fairly constant coverage. But if you go forward in time, this is the end of the century, and this is the low emission scenario. So we're down to 3 to 6 days out of 30, a tenth of the time. And then under the high emission scenario, our region right here, we have what we now have, which is almost no snow cover over the course of the winter. It just doesn't stick around. If it does snow, it's melted by the next couple of days. If it doesn't fall as snow, it falls as rain. And this is right where we are. And you can see that, in fact, up here, we're still looking at something like half the days. In fact, these regions where you'd go see in New Hampshire, Vermont, Maine, they lose half of their snowpack by sort of in the next 40 years or so. So what would be 3 months of snowpack is now turned into a month and a half. And again, it's intermittent. So another way to visualize this is this. So this is, if you took the historical period, where would you have at least 30 days out of a whole winter? Just 30 days out of a whole winter with at least some snow cover under current conditions. And New York has 30 days. We would have 30 days out of a 3-month period, even down into Pennsylvania. But given the warming of the climate, the fact that when snow falls, it will melt. When it doesn't fall as snow, it falls as precipitation. And 30 days, a third of the time, you actually have cover even up here. And so, needless to say, ski resorts look like this, unless you make snow like Blue Hills does. It's much worse if you do cross-country skiing, because it's really hard to make snow. I don't know if anybody cross-country skis. I live near what's the one in Weston where they really do a lot of snowmaking.
Yeah, right.
It's a golf course, and you could ski the whole golf course because there was natural snow. and they run a whole bunch of, almost all of the schools run their cross-country competitions there.
Yeah, it's in
It's
Weston,
the
right?
only place that has the snowmaking capability to keep something on the ground. And then turns out snowmobiling is a bigger industry for New Hampshire, Vermont, and Maine than skiing. Again, just like cross-country skiing, given the terrain, I mean, given you just can't make snow for snowmobiles. And so people are selling their snowmobiles. The winter economy that's based upon snowmobiling is really starting to shudder. But that's because you end up with these kind of conditions. And you can look outside and will not see an ounce of snow on our ground right now. So that's just an expectation of what is going to be more common than not as we move forward. If you like hiking, well, this was hardiness zones, where you can plant things. If you keep track of hardiness zones as far as planting in your yard, needless to say, they're all going to shift north. So what you could plant down here historically, well, maybe now in our region here, would be the same thing you could plant historically through this region. So if you do any gardening, what you can plant is going to start to shift. But more importantly, if you like hiking, particularly in the Blue Hills or Adirondacks or anything like that, the species you're going to come into contact with, again, this concept of migrating climates, given that our climate is going to become more like mid-Atlantic, the Southeast, all of our typical plants that we normally experience, the ones that produce foliage, the evergreens, are all going to be replaced by oak. So our plants, what we would typically hike through in the Adirondacks, something like this with the evergreens, is simply just going to be replaced by oak. And our forests are going to look like this. They're going to have this sparse one evergreen, and everything else is going to be native to the mid-Atlantic region. And effectively, that's oak. Some of our typical, sort of the canonical plant or trees that we see for, like I showed at the beginning, related to fall foliage, will still be found around the higher elevations, but sort of higher latitudes of Vermont, but they won't be here in Massachusetts. This is the type of greenery you'll be hiking, well, either you or your kids or your grandkids will be hiking through in Blue Hills, again, anywhere in Western Massachusetts. So the very sort of canonical ecosystems of the Northeast are going to shift dramatically. The other thing that's going to happen in the Northeast is a lot of the pests that destroy forests are going to start to migrate further north. And the main one for us is what we call the woolly adelgid. When woolly adelgids move into your region, and you have infestation, they turn a forest that looks like this into a forest that looks like that. And it turns out that their northward extent is limited by wintertime temperatures, but because those wintertime temperatures are going to be increasing, it allows them to expand further north. So people can actually look at where are we going to find these woolly adelgids? And currently they actually are here. They started down in Delaware. They are here, although they haven't been doing as much damage to our region. But with the warming temperatures, even under with the high emission scenarios, they're going to reach all the way to the top of Maine. All of those regions are going to be susceptible to effectively this type of transformation. And so, again, what you end up hiking through is going to be fundamentally different, both because the ecosystems are going to change due to sort of hardness of plants, but also what they're susceptible to in the forms of pests. So we'll go with that. So this has been, I don't know what time it is. Oh, I've taken up too much time. So this has been a brief overview of sort of the impacts that climate change could potentially have. It's not a done deal. As I said, some of the choices that we make now will influence whether we end up on the low emissions trajectory or the high emissions trajectory. And in fact, I haven't shown it, but the greatest uncertainty of where we end up and the impacts on the Northeast really are our choices, both as a global community. Oh, I didn't do fisheries. I forgot I had fisheries. Guess what? I won't stick around. I'll just verbalize this. Cod will not be in Cape Cod. The waters will be too warm. Lobster won't be in Cape Cod. So already lobster fishing in sort of what am I thinking of? The region off of Massachusetts is moving to Maine effectively. Cod is going to do the same thing. The fisheries, just the temperature limitations of both lobster and cod aren't amenable to the increasing temperatures. And so, again, another canonical image of our Northeast as far as fisheries is going to, or at least Massachusetts, effectively disappear. And simply because of the water temperatures that accompany the increasing change in climate. So, as I mentioned, there are options for us out there. I'm not going to go into all of them. It turns out that a lot of these options are already in place. We just have to sort of have the social, economic, political will to implement them on a global scale. Certainly here in the United States, but also here in Massachusetts. And Massachusetts has certainly made a strong commitment to renewable energy, to low carbon fuels, efficiency. Carbon capture is outside of our hands. That one's a future process. But I will also say that it's in individual hands, and I just want to emphasize something important about that. There are very low-hanging fruit as far as being carbon conscious. And one of the ways to think about this is if we want to change our trajectory globally and individually from that high emission scenario to the low emission scenario, one of the requirements is that we take our current emissions, which doesn't really matter, but let's say it's about 10 gigatons of carbon dioxide per year, that's globally, and to switch to the low emissions scenario, we need to effectively we need to reduce that by 80%. We need to reduce our current emissions of 10 gigatons, you don't need to know the unit, to about 2 gigatons for the next 40 years, which seems really, really difficult. Except, and this is the beauty of compound interest, unless you have a credit card debt, to do that, you only have to reduce your emissions individually by 3% per year. That's all it takes. And there's some really low-hanging fruit. So half of individual emissions currently is transportation, a third of it is transportation, a third of it is heating, and a third of it is electricity. That's about, for an individual, that's where our emissions come from. Transportation, heating, and electricity. If you go out and buy a car that is twice the gas mileage of your current car, that one purchase, effectively doubling the efficiency of your car, is equivalent to buying 5 years of reductions. If you do it 15% times 3 to get to 15%, that is 5 years. And all of a sudden, just with that one purchase, you've bought yourself 5 years of emissions reductions. The other one is refrigerators. They're the biggest use of electricity in any house. Go get a high efficiency Energy Star refrigerator next time you purchase one. And again, you're looking at about a 5-year reduction. So it's really pretty easy to do if you're just conscious of in each purchase as an individual. Thinking about, okay, what's going to get me 3%? 3% a year is not hard, reduction. And if you do that, 30 years down the road, you've met your 80% reduction. So I do want to end on that note. It really is our decision, whether the community as individuals, whether we follow that high emission scenario or trajectory, or we follow the more moderate low emissions scenario or trajectory. And that one really is collectively and individually in our hands. So I will end with that. I know I went a little longer than I should have.
No problem. No problem. We left it, and we still have some time.
Okay.
It's been less than 60 minutes, and we always like to leave a little time for Q&A.
Yep.
Thank you so much, Bruce.
No problem.
It's kind of scary, especially because I love snow skiing and ice skating, and I only ice skated for 2 hours last winter, but it just happened to be 10 below zero for one day. Was one of the most extreme cold snaps in my life, but only lasted 7 hours. So we will take some Q&A next in the chat, in the form of a chat. So let's see, we've had
moderate that one.
Yeah, right. So will the people want to see, our viewers want to know if we can get a copy of all these graphics that you've shown?
Oh yeah, of course.
And I guess we could put them either on your website or our website or both.
I think it
So
would be
yes,
better
we
for
will
your
we will
website.
make these available.
Yeah, I can give you the PowerPoints. If I give you the PowerPoints, then people can pick and choose graphics that they want to pick and choose.
Right. So we'll probably we've made a recording of this podcast or webinar, whatever we call it. And so when we post that, we will also post a link to your graphics.
Yep.
Let's see. What else? Let's see. Is there a role to deliberate particulate emission to negate global greenhouse impact?
There is what they're getting at is solar modification. So there is
Putting a shade over the atmosphere.
Yep. So it turns out one of the influences of human activity is obviously emissions of heat trapping gases. Another influence is what we call aerosols, particulates, solids and liquids that are suspended in the atmosphere. And their effect generally is to reflect sunlight back to space so it doesn't get absorbed.
I don't
so
like
there
the
is
sound of that at all.
discussion in
We did that in the 70s, 60s, and 70s.
Yeah. Well, there has been discussion that if global warming is so egregious, could we start sending rocket ships up above the troposphere, above the weather systems? Because you got to get above the weather systems, otherwise it would just get washed out instantaneously, well, within days, and inject aerosols up in what's called the stratosphere. There's two problems. They'd still get washed out. So you would continuously have to supply aerosols year in and year out. You don't just put them up there and they stay there. They get washed out relatively frequently, and you would just have to constantly supply on a global level these aerosols to space.
Okay, so no.
Yeah. And the other thing is, while they might mitigate temperature, they actually have a really negative effect on precipitation, where they're going to dry out the deserts more. And so they have these unintended consequences.
Right. Like I Dream of Jeannie said a long time ago. What is considered a safe level of CO2? Who determines that? And what happens when we reach that level?
So it's certainly, it's a continuum. There is no, I'm not going to go with a level of CO2. I could give you the level of CO2. Right now, level of CO2 of 450 parts per million would warm the globe by about 1.5 degrees Celsius. The 560 parts per million would warm the globe about 2 degrees Celsius. The 900 parts per million would warm the globe by about 4 degrees Celsius. Now, going from 1.5 to 2, there's gradations. I mean, it's not a step change. It's continuous. Okay, so the world's governments last met in Paris in 2019 and tried to come up with some, based upon science, some safe level of CO2. Effectively, they said we really, really want to avoid 2-degree warming or above. So that set what they call the guardrail. They really do not want to get above 550 parts per million. Then they also said we'd really, really like to keep it below 1.5 degrees Celsius warming, which is around 450 parts per million. So this was the world's governments. And each government came up with their own plan to how they would meet some target that would allow the globe as a whole to either hit 450 parts per million or 550 parts per million. None of us have met those goals. The US hasn't met those goals. No country. We all swore we were going to meet these goals, and nobody's done it.
Okay, Gregory asked a question about that too. So I think, Gregory, we're answering your question now too. Okay, Alan asks, how will climate change affect seasonal allergies?
So it'll certainly affect summertime allergies. The other thing it'll affect is summertime asthma, not just because of allergies. So the warmer climates, particularly in urban areas, are going to have much worse ozone near the surface. Twice as many, what are the days called? Dangerous ozone conditions or pollutant conditions. So those are expected to increase by twofold, especially in urban areas.
So bad.
Yeah. So there's that. That's not allergies. It does turn out that the things that grow best in warm weather are weeds. So,
good.
Yeah. So it turns out that allergies are going to get worse because a lot of the things that can actually survive the warmer temperatures are not the sort of traditional flowering plants. They're going to be all the weeds that produce pollen and allergens. So the expectation is that because they have a better threshold for surviving, they're going to be more preponderant. And so allergy is expected to go up as well.
Jeffrey asks, the slide with temps over the century had a large increase in the 1940s. What was the reason for that spike?
So this was, spike.
Well, in the 1940s, that first graphic you showed the 1940s kind of flat, and then it just.
Yeah, it flatlined. So there are, I'll play this. Oh, I've got to share it first.
No, it's all right.
Oh, don't worry about it.
I'm worried. Right.
So there are natural variations. So they started to go up here. Then there are sort of what we call multi-decadal variations in the natural climate system. Part of that might have been why these started to come down here. The thing is, though, they rapidly intensified. So what we're really looking at is they started to come down somewhat, yes. And that's absolutely the case. And that can be attributed to actually changes in solar intensity. Turns out that if you looked through here, solar intensity was starting to come down during this period. In fact, solar intensity, I don't have it, is now less, it's actually lower than it was back here. And at the same time, so if we'd just been worrying about the sun, maybe we would have ended up down here. The thing is, we don't just worry about the sun. And so this one's, I think, principally solar intensity. But at the same time, the CO2 influence is just overwhelmed where we would have ended up, given our solar intensity is down here somewhere, back what it was here. That cooling effect has just been overwhelmed by increasing carbon dioxide concentrations.
Glad you mentioned the sun anyway. Let's see. We have famine here and worldwide, and when?
What's that? famine. Well, I don't think we'll have famine here. I think we'll always have access to food. It might get more expensive. Um, that said, there is the possibility that our bread basket, in fact, it's not a possibility, our bread basket is going to move into Canada. They're the ones who are going to be able to grow wheat, particularly if it gets really warm and really dry, and effectively it goes towards a dust bowl again. Maybe not that severe, but our ability to grow food in what we call our bread basket is the climate for that kind of agriculture is going to move into Canada. I'm sure they're still going to supply us with food. So I don't think we're going to run out of food, but there are people who are going to run out of food. Subsistence farmers, or if you can't.
Well, famine has been throughout history. There's been famine, and we can't fight it because bombs and politics. I think that's a different story.
Yep.
What you said about each of you needing to only reduce individually 3% per year made me hopeful.
Yeah.
What are some other reasons to be hopeful?
Well, certainly, there is, I'll see if I have another slide. The other reason to be hopeful, I'll pull this one up. Oh, I haven't been sharing, have I?
Yeah. What do you mean?
I'm not sharing a slide right now, am I?
You are not.
Good. Let's see. I'm going to pull up a different slide deck. And I'll talk to it while I'm pulling it up. The other reason to be hopeful is that a lot of the solutions that we need to get to where we want already exist. And there is no silver bullet. Let's see if this one. Oh, please tell me. Yeah, there is no silver bullet. That said, a lot of the technology we want is already out there. And we call these wedges. So I'll pull this up. So if you remember, I mentioned that how much are we emitting currently? This is our emissions. And so we're currently, actually this says 8, we're at 10. And this is since the 1950s. So our emissions have constantly gone up. And we're at about 10 now. But if you then scale that down and look where we need to go, this would be that worst case scenario. If you can read this, it says 9 degrees Fahrenheit. That's effectively that worst high emission scenario where we just take historic emissions and keep increasing them going forward as China becomes industrialized, as India becomes industrialized, as Africa becomes industrialized. That's the worst case scenario. Now, to get to a doubling of carbon dioxide, we would need to flatline our emissions, just keep them at the current values. And to get to that 1.5 degree emissions scenario, we'd actually have to start reducing them. And I don't know if you can see them, but you'll see these wedges. Each of those reduces our emissions by 1 gigaton of carbon per year. And so you'll see that none of them are like a really big wedge. Each one is a different activity, but everything in here is technology we already have. We just have to incentivize implementing it. Some of this stuff here, like carbon capture, is technology that's being developed, but isn't at the forefront, isn't currently available. But we certainly have the ability, if we incentivize it, to follow this trajectory and eventually get down to here. So I think the other hope, the reason for hope, is that a lot of what we need to accomplish over the next 10 to 15 years, just to even go from this trajectory to this one, is out there. But there is no silver bullet. It's multiple mitigation strategies. Some of it's economics, some of it's population, well, not population, but education. If you go out there they've gone through and what's the most efficacious way of reducing emissions. Education of women turns out to be the number one. As soon as you increase the educational capabilities of women across the world, you end up reducing birth rates and just it's not
What?
reducing them below zero.
What?
It's what?
What?
Yeah, it is.
Huh?
They've done all these studies for social, economic, agriculture. It's not necessarily, but because I mean, we in the U.S. probably don't. That won't work for us. But on a global scale, it's not saying take the population below what it is today. Just don't let it increase as quickly as it's projected to increase. Yeah, that's that is one of the wedges in there. But it's also one of the most efficacious ones, especially for developing nations.
All right, let's shift gears here.
Okay.
Seems like the sort of deck should be mandatory. This sort of deck should be mandatory K-12 education since it's younger generations. How would you rate how well society is educating the young folks in this area today?
Um, Europe's doing a pretty good job. Europe's doing a very good job. I'd say this would be basic knowledge for almost anyone graduating from high school in Europe. It's not in the US because each of our school systems is state run. So in fact, a lot of this discussion is, where was it that it was being prohibited and from the state standards? Oh, I just was reading about it where it gets caught up in a whole bunch of politics. And so because all of it's state mandated, it's actually being taken out of the state standards instead of being mandatory. In Massachusetts, they're actually, I think they've just started to implement it as a state standard within the last year or two. So unfortunately, the way the sort of political system set up in the US, we won't have the same universal coverage the way they do in Europe, for instance.
Okay, so we're pretty much now at over 40 minutes. Let's see, are we about out of question? That was interesting. The quiet part was just said out loud. Humans emit 40,000 ppm every time we exhale. We are big carbon emitters. Less human on the planet will be better for Mother Earth.
Well, no, it's not. So I do want to emphasize this. It's not our emissions by breathing. Almost all of those emissions that we breathe out are taken up by plants. It's the human activity. It's burning fossil fuels predominantly. Effectively, what we're putting into the atmosphere right now is not our breath that matters. It's all the organic carbon that we've dug up from millions of years of effectively decomposition, whether it's dinosaurs or whether it's forests. All of that organic carbon gets converted underneath our surface into coal, oil, gas. So we're digging up millions of years of stored carbon and putting it into the atmosphere over the course of 100 years. It has nothing to do with our breath. It has everything to do with how much industrial activity to some extent.
Gotcha. Right. All right. So we'll just make this the last question here. If we are truly such dire situation, why? He says, why is nuclear power? But I think where is nuclear power? Why are we not implementing nuclear power?
Our people certainly are now recontemplating. So if I went to one of the slides that it said low carbon energy, the image on that slide is a nuclear power plant. And people are definitely rethinking it. In the US, part of the problem is that it's because of the regulations from when nuclear power was really not as trustworthy as it needed to be. It's really hard to build a nuclear power plant in the US. And it's actually a lot easier to build a dam It's a lot easier to build offshore wind farms or implement solar panels. Those things are a lot easier to get built than a nuclear power plant. It's not to say nuclear isn't on the table, it is. It's just not going to be rapidly on the table.
Right. And this whole thing with Yucca Mountain, that's probably another whole story someone just asked about, right? We were building that waste facility there, and it just got totally red taped. So that's a good topic for the future.
Yeah.
Bruce, this has been very enlightening, and you certainly stirred up a little bit of a hornet's nest here,
Well, I hope
as
not.
far as just scaring us.
Well, that's why I tried to end on this concept that it is in our hands where we're going to end up, both collectively and individually. And there are options out there where we do not have to end up in the most sort of scary scenario, and we can mitigate a whole bunch of what could happen, and that's all in our hands. So if we're proactive about it, all those 100-degree days won't happen.
All right, so we'll probably post this on bluehill.org, and you can find
Why don't I
Bruce.
send you the newest version, because I made a few slight edits, but I'll do
Okay.
that tomorrow.
Yep. So we'll put these slides online, and we'll share it on bluehill.org. And people are saying thank you, thank you, thank you.
Well, thank you guys. I really
You're
appreciate it.
welcome.
If there are any follow-up questions, feel free to email.
Oh, yes. And always come up and visit us at the
Yeah.
Blue Hill. We've got a new and improved facility.
Yeah.
And we'll have days that we're going to be there. So we'll announce those days, and you can come up and we can all discuss it in person. That'll be even more fun.
Yeah.
And and you can see all the weather records. It's all right there.
You can track this stuff.
All right. Thank you very much, Bruce.
Thank you for having me.
You are. It's our pleasure. Thank you, everybody. We'll see you
Have a
next
good
time.
evening. Bye.
Bye.